In previous modules, we've looked at shorts between wires and the bus, shorts to ground, and shorts to voltage. This time we'll have a look at the diagnostic procedure for an open circuit. Using a scan tool, we'll see what modules we can communicate with. I have found that I can't communicate with the park brake control module or the rear differential control module. As with any bus diagnosis, it's necessary to start with the correct schematic for the vehicle you're working on. It can be seen here that both modules are at one end of the bus. The problem could be an open circuit in the bus wiring or a fault in each of the modules. It's easy to check an open circuit in the bus wiring. This is done by doing a resistance check across pins 6 and 14 on the DLC. And remember, there's to be no activity on the bus when you take the measurement. This will make sure that you don't get an incorrect reading. To check to see if the bus is asleep, I'll connect my voltmeter between pins 6 and 14 on the DLC. I've got 0 volts. This means that the bus is asleep. So I can now go and do my resistance measurement. I should have 60 ohms. That's two 120 ohm terminating resistors in parallel. I've got just over 120 ohms. That indicates that there's an open circuit on the bus. From the schematic, it is possible to work out the general location of the fault. We can communicate with the engine control module, the transmission control module, the electronic brake control module, and the body control module. So the open circuit can't be in this section. The open circuit must be between the body control module and the park brake control module. So where's the best place to start? Looking at the schematic, we can see that there are 4 connectors between the body control module and the park brake control module. You can start at any connector. I'll use X201 because it's the easiest to get to. After disconnecting X201, it will be necessary to test the resistance between pins 45 and 35 on both the male and female side of the connector. If the reading on the male side is 120 ohms, then that will be the terminating resistor in the engine control module. If there is an open circuit here, the fault must be in the wiring between X201 and the BCM connector, or an internal fault in the BCM itself. I've got 120 ohms on the male pins, so I'll check the female pins. Many technicians will only check one side, and if the fault is not there, they will incorrectly assume it must be in the circuit on the other side of the connector. I always check both sides of the connector, and if my readings are correct on each side, then it must be the connector. If it's the connector, you would need to check the terminal tension on the female side or corrosion on either side. If the reading on the female side of the connector is open circuit, then plug the connector back in and look at the schematic for the next possible test point. X404 would be the next connector. The previous process is repeated on this connector. These results indicate that the fault is further down the circuit. The next connector is the park brake control module. The same procedure is repeated on this connector. I'll connect my test probes to terminals F and L and measure the resistance. (120 ohms). I'll now move the test probes onto G and K and repeat the test. (120 ohms). So that means either side of this connector I can see the terminating resistors. So the fault now must be in the module itself. I can prove this by checking the resistance between pins L and K and pins F and G on the module. I have an open circuit between pins F and G. That confirms the fault is in the park brake control module. Let's take a look at the high-speed schematic for this vehicle. This circuit uses bus topology, meaning that there is a module at each end of the bus. These modules also contain the terminating resistors. All the other modules are connected to the two wires joining the two end modules. If there's a break in the main bus wire, then the communication will be lost between the modules on each side of the brake. An open circuit at this point would prevent the scan tool from communicating with the transmission control module, the steering control module, and the skid control module. The resistance of the DLC will be 120 ohms. I've connected up a scan tool and run a system search, and as you can see, there's no engine control module. The next thing I need to do is check the resistance between pins 6 and 14 on the DLC with the bus asleep. I'll just turn off the ignition. With the ignition off, I now wait for the bus to go to sleep. With the bus asleep, I can check my resistance. It should be 60 ohms. And I've got just over 60 ohms. So that means the main two bus wires are intact. So where to from here? For a module to communicate, it needs comms, a 12-volt supply, and a ground connection. Some modules like this ECM use multiple voltage supplies and grounds. When checking the modules, it's necessary to check them all. I've checked all the powers and grounds to the ECM, and they're okay. I've got 60 ohms at the DLC. That means that the bus wires are intact. So the fault must be the module itself. If there's an open circuit in a bus wire going to one of the modules branching off the main bus, a resistance check will not reveal the problem. As you can see here, there's no break in the wiring between the DLC and each of the end modules, so the resistance will be 60 ohms. It will be necessary to check the continuity between the DLC and the module. When doing this, don't forget to check the connector on the module as before. If the comms wires are okay, then check the module for battery and ground. If these are correct, then the fault must be in the module. Open circuits in a bus system are not difficult to diagnose as long as you follow a systematic approach. Don't jump from one section to another. Use your initial readings plus the correct schematic to formulate a plan of attack. Don't guess, diagnose. And remember, training is the key to your success. Bye for now.